Hey everybody, welcome to the stream. It's so great to see you. I'm here, Stephen, logging on, and I have the owl friend today. Oh gosh, that's the wrong direction. There it is, my owl friend over there. Um, we're gonna teach you a little bit about forests. I don't live in a forest, but my owl friend does. Yeah, that's why I brought them along. So anyway, is anyone there online with us? Please feel free to give us a chat, any kind of comment. If you're liking the streams this week, where are folks logging on from? How late or early is it in your time zone? Would love to hear about it. But in any event, we're going to be learning today about machine learning and how you can potentially use machine learning for social good. And the example we have for today is forest management. This is actually a workshop that I presented last month at the Global Hack Week for AI algorithms, but I'm going to be presenting it again today. If you have not checked in, I want to make sure that everybody checks in because it's going to help us keep track of what kind of content folks are interested in. So I just sent a link, and if you could check in for the event, it would be super, super helpful for me. And also get you some points for your local community in our Global Hack Week for your guild. So I see a few hellos from the chat. Hi, shout out to all of you. And I am Victor says it is 7:30 a.m. in India. So getting a nice start to your morning there. I see. That's great. I'm glad you chose to start off your morning with some major league hacking. But anyway, has anyone heard of this concept, reinforcement learning, or any algorithms that are associated with reinforcement learning? It's very common to use actually in robotics, in the field of robotics, and also in the field of policymaking when you're trying to make a decision for the government or for a company. See another person say hello from India. Hi there, Rahul. Good to see you. And I am Victor says Q-learning. Yeah, so actually we're going to use Q-learning today. That's a really good example. We can totally use Q-learning today in our workshop. And Q-learning is just one of the algorithms that come under reinforcement learning. Reinforcement learning being a field that is kind of halfway between unsupervised and supervised machine learning. In reinforcement learning, you are trying to get the computer to find the best strategy, but you don't give it training data. You might give it some kind of scenario, which we call a policy. And so that's kind of the goal for today. Let me share my screen and show you all what I'm talking about. Let's see if I can get it to share. You know, I always forget to put the actual screen up in the slides, but this time I'm remembering. So I'm super happy about that. Last time I gave this workshop, I was constantly losing the screen, losing track of it. And, you know, we always have room to grow and improve. That's one of the themes of Global Hack Week. So I hope to improve a little bit today for all of you. Okay, so, you know, we're starting off with the title slide, which is called Markov Decision Process Algorithm. And this algorithm is a powerful one because it makes use of a concept called Markov chains. Has anybody in the chat heard of Markov chains? If you have, feel free to chime in and give us a little explanation of Markov chains. I'm actually going to present the Wikipedia page for Markov chains. I actually think it's really helpful to look at the Wikipedia page. Your teachers might not like it, but I quite like it because they come up with great diagrams like this one here. So a Markov chain or a Markov process is a stochastic model. And what does that mean? Let me share it with you. The stochastic model is a statistical model. So it's not determined. That means that there's no final word on the outcome. If you arrive at the airport, for example, for your flight, and you have a ticket to get on the plane, that means that you are determined to get into your seat. There's no possibility that the airline will tell you, oh, by the way, sorry, you can't get in your seat, even though you paid. So that's kind of a determined way. But if you think about it in a more broad sense, there's a possibility that your car might get a flat tire on the way to the airport. There's a possibility that the plane might experience some kind of malfunction and you can't get on the plane. There's a possibility that your luggage might be too heavy and you have to take some time to get rid of some items in your luggage, and maybe you missed the plane. So that's more stochastic because we can't really predict all of that stuff. We would just use a random process to model it. And that's exactly what a Markov chain is doing. The reason they call them chains is because of these great diagrams that people will draw. And we're going to draw one of those today, a Markov chain. So these are two states, which is the base unit of a Markov chain, state E and state A. You can also call them the blue state and the gray state. And there are many transitions between the states. So you could take this orange arrow to state E from A. And if you're already in state E, you can take a transition back to state E. So just stay in your spot, kind of like musical chairs. And we assign a probability to each of these states. So the first one would be 0.3 or 30% chance that if you're already in state E, you stay there. And then we have another transition that goes from E to A, 0.7, so 70% chance we go to point A. And that's kind of a way we can model the world. So we have a comment here, AXP, saying it is a mathematical system that experiences transitions from one state to another according to certain rules. And that is a really great description of a Markov chain. So it sounds like our audience is catching on. That's really good. Does anyone have any questions about this Markov chain stuff? If you do, post them in the chat. I'm more than happy to answer them. Also, if you would not like me to highlight your comment, you can just write a little "don't highlight" next to your comment, and I will not put it up on the screen. I know some people might not want that, so if that's the case, please let me know. Okay, let's move on. We're going to switch to our slides once again. And we're going to focus now on the Markov decision process algorithm, which is a way to use Markov chains in a machine learning context. So as I said earlier, Markov decision process is a reinforcement learning algorithm. And what it does is this process designs a policy to fit a scenario. And what that means is that you could find yourself in a scenario like the airport that I was mentioning and have a policy to optimize your experience. So for example, maybe your policy to get on the airplane quickly is to check your baggage and make sure it's the proper weight before you arrive at the airport. And then another policy that you could have is to choose the security line at the airport, which has the shortest width. And maybe you have a long security line, short security line. You want the short one, right? Because you're smart. You've got your policy, and that's what the decision process is doing. And not every situation is as simple as just waiting at the airport for your plane. You can have a really complicated one. Like how do you write tax system in your government? Um, or how do you run a business to make sure the profits are as high as they can be? And how do you tell a robot to build a car? So these are scenarios that you can design policy for. And just in case the scenario is a little unclear to you, a scenario, we're trying to use this Markov chain to really build that out and say, okay, scenario is states plus transitions plus actions plus outcomes. And here is our first example of a Markov decision process. And we have San Francisco to Los Angeles. These are two big cities in the US where we have much travel between. San Francisco being Silicon Valley, where all of the largest tech companies in the United States are headquartered, and Los Angeles being a place where many film and Hollywood entertainment movies are made. That's where I live. I live here in Los Angeles. So if I was visiting San Francisco and I wanted to get back to Los Angeles, I might need some kind of policy to get back as fast as I could. And these could be the two locations, but we need a way to go from one to the other. And I've written up three different possibilities. So we have plane, which is probably the fastest way to get between the two cities. They're pretty far away, and even by plane, it could take an hour and a half to get from one to the other. On the other hand, the car, you can take what we have in California, the state route, Interstate 5, and Route 5 will take you 6 hours to get from San Francisco to Los Angeles if you're traveling at the speed limit. Then we finally have the train, and the train is really slow compared to these other methods. We do not have high-speed trains in California, so it's going to take you 11 hours to get from San Francisco to Los Angeles. And at that rate, you might as well just stay in San Francisco until you need to visit the next time. But just kidding. We definitely want to get there. So, the plane would be our best case to get there as fast as we can. But let's add some complication to our model. So, with the car, we have a chance of running into some traffic. And let's say that it's a 10% chance, because we're not going to run into this traffic every single time, but we will run into it sometimes. And that 10% chance could add an hour to our trip and make it a 7-hour trip. That's a lot. Let's go to the next one. The plane, oh my goodness, so many things can happen at the airport. The plane ride takes an hour and a half, but there's a 10% chance that you'll have a security delay of 2 hours. And then after you experience security, you may have a plane delay that could last up to 3 hours, 25% chance of that. And then a 5% chance of a deplane delay. So this is after you've disembarked off the plane in Los Angeles, you haven't disembarked, but you've arrived in Los Angeles on your airplane. You could spend an hour waiting for them to open up a gate so you can leave the plane and get into the airport. So there's a lot of things that can happen on that journey. And I'm sorry about that. The ordering was a little off on that last one. So I want to ask you all a new optimization question, which is that what would you choose if you needed to get to LA in 8 hours or less, but you also want to get there as fast as possible? So you cannot wait more than 8 hours. Let's say you have a really important business meeting, and if you arrive 10 minutes late, that's going to be terrible for your business. Or maybe, you have an exam in Los Angeles that you have to take, and the exam's only offered once a year. And if you miss it, you have to wait the next year to take it. In this case, would you take the plane? I want to hear folks' comments on this. What do people think in the comments? Which pathway would you choose? I'll give you a few minutes to think about this, because it's kind of a hard question. Go Rob says a car. Okay, car. And a lot of people actually say car. We have one response which is a little more theoretical, which I like. Choose the route with the lowest expected value of travel hours. And I would invite you, KVN, I would invite you to maybe explain a little bit what you mean by that for those folks who might not know what is expected value. But I will also look into that. We have one person say plane, and I'll just note that if everything that could possibly go wrong goes wrong, so if you get a security delay, a plane delay, and a deplane delay, that will add up to, let's see, 5.5 plus 1.5, that's 7, plus 1.1, that's 8.1 hours. And if that happens, then you miss your you miss your exam or your job interview, and that would be really bad. So maybe we don't want to take the plane, because we have that very small chance to be completely off. But I like what you all are thinking. Thank you so much for the comments. This is a little bit of a trick question, actually, because it's kind of both plane and car. So let me show you my solution. The car would be great if you need to get to LA, because you'll always get there less than 8 hours. But there's actually a faster way. Yeah, this is good. It has a 0% probability of taking more than 7 hours, just as AXP says. But you know what? Actually, the optimal solution is the following. Go to the airport. Go to the airport first, and go to the security line and stand in the security line. Because if you get through the security line in 1 hour or less, then there's no chance that your plane ride will take more than 8 hours. But if it takes an hour or longer to get through the security line, as soon as you hit an hour waiting in that line, you should run home and get your car and drive straight to Los Angeles, because then you're going to make it in exactly 8 hours. But the majority of the time, 90% of the time, you will not experience a security delay. And if that happens, you'll get to LA way faster than the car ever would. Okay? And so that's the actual solution for this scenario that we've designed. And, some folks might say, well, wait a minute now. If you do that, then you're going to spend a lot of money on a plane ticket, because you have to buy your plane ticket before you go to the airport, right? But you know what? We're not optimizing for cost. We're not saying find the cheapest way. We're saying find the way that will get me to LA as fast as possible, but it can never take more than 8 hours. Okay? That is our optimization problem. And sometimes these optimization problems are not always intuitive. And that's one of the main reasons why we use machine learning. We use strategies that are not necessarily good for that. Oh, and then this is a really good point. The Jindal, time for going home. That's a good point. Maybe we should leave. Maybe we should add that into our model. Maybe we should add that into our Markov chain. A little bit of time that it takes to go home. Uh, you can make your Markov chain really complicated. You could add so many different states. A state for being at the airport, at the airport bathroom. Maybe you need a bathroom break. That would be a good state to add in. You could have like hundreds and hundreds of different states. Um, it's always just a matter of how complex do you want your model to be. Um, yeah, exactly. We could add car breaking down. We could add car breaking down, and there's maybe a percent chance of that. Um, that's a really good one too. So we can always make our Markov chain model more and more complicated, and the more details and information that we add to our model, the better its success will be at devising the optimal policy. But I really love the comments from all of you. Thank you so much for providing those. I like this one too. A part says fueling the car at checkpoints. That's another really good one. Because we didn't consider that, but and depending on how many times you need to refuel, do you have a car with a small tank, a big tank, who knows? But that's certainly something to consider. Okay, so we're going to assign some states into this, and you can see that those states are represented by S sub 0, S sub 1, S sub 2, and so on. These are how we can talk about our travel problem in a more formal mathematical sense, right? So we can kind of formalize what we're saying here and say, instead of saying San Francisco, California, we'll just say S0, state 0, because that's really all we need to know from a mathematical perspective. And in this particular model, we have 8 states, but we can have arbitrarily large number of states. And have Anurag in the comments saying, hi, hello, good to see you. And a question from AXP. If we add too much complexity, will we not encounter a problem like overfitting in supervised learning? And, that's a good question. I mean, we do not have the same sort of problem of overfitting as we do in supervised learning because we're not training a model based on human-fed examples or an example data set of any kind. If we add too much complexity, we could risk overestimating the skill of our model, though, because we add so many different states and transitions that we think, wow, this model is perfect. But actually, no, we're not going to arrive at a perfect model ever. And also, our ability to find the optimal policy is only as good as our solving algorithms. So back at the beginning of our workshop, I.M. Vixter said Q-learning as a possible algorithm. And Q-learning is a great algorithm, but if we don't run it at the optimized way, we might not arrive at the best possible solution. Even if we have the perfect Markov chain. So you're only as good as the algorithm you choose to solve. Okay, so we've added our states, our numbers of states. And another question, is there any way to train this model more fast with an optimized way? And there are many algorithms that you can try. We'll get into that actually. We're going to show you a algorithm toolkit called NDP Toolkit that's available in Python and allows you to solve your Markov chain for the optimal policy using many different algorithms. So I would recommend trying several algorithms and seeing which one gives you the best result in the quickest fashion. But the short answer to your question is that yes, we can pick an optimal algorithm for the use case that we have. But let's continue with our formalizing of this Markov chain. And we're going to call something the state transition matrix. So this is actually one of the bread and butter tools we use to implement Markov decision process. And the state transition matrix we sometimes call P. It is a list of probabilities that one state will transition into the other. So for example, we have row 0 in the top and row 1 in this second row here. And then we have columns 0, 1, and 2. So we call this example probability P12 because it is in the row 1, which is the second row. I know that's a little confusing, but we always start at 0 in computer science, or most of the time. And and then we have column number 2 here, P12. And what would say, another college level lecture. I love it. I hope you are enjoying the college level lecture style. But if you want something different, I'm always open to feedback. That's just my favorite kind of lecture. So I hope you're enjoying that. But in our case, the probability of severe traffic if a car is chosen is the state 1 to 2. If we go back to our diagram, we have state 1, we're in the car, we're on our way, and then state 2, if we transition into state 2, that means we've hit some severe traffic. So that's 0.1. Then we have our rewards matrix. This is the next one that we have. And before I mention that one, just want to say hello to Armand025. Hello, good to see you. Anyone's welcome. Join anytime and tell your friends. We're having Global Hack Week all week long. This is just the first workshop that I have planned on applying machine learning to cases where social good is involved. And so in this workshop, we're learning about how forest management might be benefited by machine learning. So now we're studying the rewards matrix. And so the rewards matrix is the second component that's important for the Markov decision process algorithm. The rewards matrix tells us that for each action, if we're in whichever state, we can find out what's the reward for that. So for example, in our case, the reward for starting from San Francisco, which is S0, and choosing train S6. So if you go into train, then you will get 11 hours as your quote unquote reward. And what that means is that you're going to experience 11 hours of travel by choosing that. And we're trying to optimize for travel. So that's why the rewards matrix is structured to show time taken. And in this example, we actually want to minimize our reward. And it doesn't really matter whether we minimize or maximize our reward. It's just a matter of optimizing for that. So let's move on and talk about our social good example, because this is Social Good Week. And what I have prepared for you all is an example on forest management. So before I go into this, I want to actually ask, do people in the chat have any ideas for us on other ways that we could apply the Markov decision process for social good? Does anybody in the chat have an idea that's not forest management? It might be some other way we could apply this technology to have an impact. I'm really curious to know because we have a lot of us here, and I think maybe some of you will have a really good idea. We have some ideas for neural network, definitely. Social science, totally. Carbon impact tracker, that could be really interesting. How do you optimize your carbon impact? Minimize that one. Our rewards matrix could be carbon. And making unbiased jury panels, that's super interesting. How do you choose the optimal jury? I don't know. Good questions, very good ideas. But in this case, we'll just study a more simple case, which is this really funny forest that I've created. It's a really simple forest. And it's actually, I didn't actually create this idea. It's an example from MDP Toolkit, but I've sort of adapted it for this workshop. So let's build a state diagram or Markov chain for the forest. And the first state we have is our new forest. So S0 being that state. And I've put a little tiny tree for you to denote that. But basically, this new forest is where we begin our journey in the forest. And the next one would be middle-aged forest. So maybe after 1 year, let's just say in this magical forest where things grow really fast, we go from a new forest to a middle-aged forest. And now it's 1 year old, it's grown a little bit bigger, it's a little more wood on the trunk, so to speak. And we have our S1. The final state for our forest is going to be S2, and that is our mature forest. So with the mature forest, we have a lot of growth, a really big tree, and that would be awesome for us to get a mature forest because we can do a lot with the mature forest. Okay, now I want to mention the transitions that we have because every Markov chain needs an actual chain, some kind of transition between the states. So the first one I'm going to mention is the probability of growth. And we're going to say that that probability each year that the forest continues to grow is 90% or 0.9. And why, you might ask, why is there only a 90% chance of growth? Couldn't we say 100% chance? And the reason is that something could happen, something kind of catastrophic for this tree, which is that there could be a fire, a forest fire. And there's just a 10% chance of that happening. But if it were to happen, then we would lose this tree and it would go all the way back to a new forest where there's new growth and we start all the way back from scratch. This process can also happen with the mature forest. And actually, I meant to draw this arrow all the way to the new forest. I only drew it to S1, but really, if there's a fire, this tree burns down and it has to start from scratch. It has to start from S0, not S1. So, actually, I'm going to change that really quickly because I don't want anyone to be confused. Just give me 1 second to change that so that no one is confused. By the way, if anyone has any questions, please feel free to mention those. I'm totally happy to take a question about the method or about anything regarding that. But let me go through our forest again. We have our 3, and our transition for S2 actually brings us all the way back to S0. Okay, and that could be an example of a forest fire. So we have our probability transition matrix for this simple forest. We could actually add an arbitrarily high number of states if we made it really complicated. We could put a state in for every single year, maybe for like 100-year tree forest. We could add in summer season trees, winter season trees, because there is a difference in the growth actually between those two because of the rain and the heat. But for now, let's just keep it really simple with our forest that it grows to a mature forest after 2 years, 2 short years. Okay, now I want to talk about the rewards matrix. And this rewards matrix is how we define our rewards for being in certain states and making certain decisions. So in this case, we've made the decision to cut down our forest. And when we cut down the forest, of course, we can sell the wood from that tree on the market. And I've written a few values below. So the S0, the new forest, is just a little sapling. And so we can't really sell that for wood on the open market. It's just a little twig. But if we have our middle-aged forest, we can get $1, let's say, for that middle-aged forest. That's pretty good. So maybe we get $1 for that middle-aged forest. And if we have a mature forest, on the other hand, that's $2. That's $2. Okay, we cut down that tree, get $2. On the other hand, we have keep. And with keep, this means that we kept the forest for another year. We did not cut any trees down. And when we did that, it didn't really give us any money, but maybe the government is going to give us $4 for maintaining a mature forest. And they say every year you keep this forest up, it's really great. The birds love it. The bears love it, and the people love it. And so you'll get $4 from the government to keep that mature forest alive. But you got to get it to that state. You're not going to get any money from the government if you get a new forest or a middle-aged forest. Okay. Someone says, do we have to make a carbon tracker using AI and ML for day one challenges? I don't actually know what the day one challenge is today, but that sounds really hard to do. I'd be really impressed if someone can do that in a day on day one. Yeah, anyway, this is our rewards matrix. And now we're going to take a 10-minute break just so folks can have some time to really let this digest in their brains. And we're going to come back with some Python and actually apply that. But all right, everyone, I will see you in 10 minutes and have fun working on that project. Oh boy, sorry about that, everybody. I was just saying, I hope you all have had a very nice 10-minute break, and just make sure you have Python installed. And I was also talking about how I was having some beans over the break for dinner. Over here in Los Angeles, it's dinner time, and had some red beans. I wonder, did folks in the chat like to eat beans? Just let me know. But anyway, it's really good to see you back. And let's continue with our example. So we're going to be using the MDP Toolbox, which is a library in Python. And you can see that the MDP Toolbox provides classes and functions for the resolution of discrete time Markov decision processes. What that means is that it's going to allow us to resolve these Markov chains. And so make sure you have this installed on your local computer. Yeah, so we're going to be exploring one module in particular, which is the example module. And this is where we get our forest management example. And so we're going to create the default example, which has 3 states. And that means that there will be 3 different classes of forest. Then we have $4 for keeping and up to a $2 reward for cutting the tree. And P is the probability of a wildfire. So by default, that's set to the 0.1 or 10%. Someone's asking for the link to this documentation. I'm totally happy to give that to you. Thank you, Dora, for pointing that out. Also, just gonna circle back to a question we had earlier from Armand about the carbon tracker, and I actually did look into that, and you're essentially right about that. I'm sorry, I just wasn't familiar with what you were talking about. But we do have a challenge, track carbon footprints. Just to let you know, though, you do not explicitly need to use AI for that one. It just needs to track a user's carbon footprint. So you do not need to use AI, but nice catch on that one, Armand. This could be a really good way to implement AI into your track carbon footprints project. So just an idea. So excellent pointing that one out. But okay. Oh, you say, can we use Flutter? Sure, that's totally fine because Flutter is cross-platform. So you can sort of deploy that anywhere. But yeah, awesome. And yes, beans are great. And Raul says we eat rajma. I actually don't know what that is, but if you'd like to, yeah, I will research that one. That sounds pretty good. Do you have to install the MDP toolbox? Yes, and we're going to install that one next. So let me go ahead and show you how to do that. We're going to share screen, and I'm going to show you a Jupyter Notebook. And so in this Jupyter Notebook, it's going to give you everything you need to know to set up with this one. And so here you go. I'm going to send you a link as well so that all of you can download this notebook and get going with it. Send that real quick. Oh, Rajma is kidney beans. Okay, thank you for letting me know about that. I actually have had kidney beans. They're really, really good. So here's the link, everybody, to the Jupyter Notebook. And you can go ahead and get started by installing PyMDP Toolbox. You use your pip install. You can do it in a terminal, or you can also do it with this exclamation point in front, and that will show you how to install PyMDP Toolbox. But that's a way to install it onto your computer. Just make sure you're running your Python 3 kernel. And yeah, once you have that downloaded, we're going to import a number of modules. So the first module I'd like to point out is NumPy or NumPy. And that is useful for all kinds of scientific learning applications. And yeah, then the second one I'll point out is MDP Toolbox. So MDP Toolbox is going to give us our example module for the forest management example, and also our MDP module, which is going to actually let us solve our scenarios from Markov chains. And yeah, we'll need both of those for this workbook. Okay, now I want to direct your attention to the forest management example. And in this notebook, I've sort of written down all of the stuff that you saw earlier in our PowerPoint presentation. So yeah, trees can be either young, middle-aged, or old. And each year, the trees get one stage older. So each year, there's a 10% chance that the whole forest burns down. And if the forest burns down, you get nothing. But if you cut the trees, you get 0 points for a young one, or $0, 1 point for a middle-aged one, and 2 points for an old one. And if the forest reaches its oldest state and you do not cut it, you will receive 4 points. So those are the possibilities. I'm going to zoom in a little bit because I just realized that it's pretty hard to see this from your perspective. But what's the best strategy given these facts? We might not know that just from our own experience. We might want to turn to an algorithm to figure that one out. So that's exactly what we're going to do, and we're gonna define these inputs. So once again, from the documentation, we have 4 inputs to our function, our example function. We have S, which is the number of different trees, ages. We have R1, which is the reward that you get when you wait, and for the forest it to be in its oldest state. R2 is the reward that you get when you cut the trees and the forest is in its oldest state. And P is the probability of a wildfire occurrence. So that's the probability that you get a 10% of everything burning down, right? So there you go. And then outputs are the transition probability matrix, which is that P matrix we were talking about. So this function is going to return that, and the rewards matrix. And so let's run this cell. We can do that by clicking run and see what we get. Okay, so let's explore the probability transition matrix. So this is P0. The probability transition matrix has 3 dimensions. So we're going to use this first dimension is going to say if the action wait is chosen. So if that action is chosen, then there is a 10% probability for every single tree level that that tree might burn down in a forest fire. And you know what? In real life, I'm pretty sure that older trees are more resilient to forest fires. So the probability might go down as you get to an older and older tree. But in our simple example, the probability is always 10%. Then we have this other interesting feature in the matrix, which is this diagonal feature of 0.9, which is the 90% chance that this tree will stay in its original state. If you go all the way to the bottom here, you see that the oldest tree can never get any older. So it always just either stays in its current state or it goes back to the new forest. So here's our probability transition matrix if the action is wait. If the action is cut, another interesting thing to look at, we always return to the new forest. So this is basically certain. If you cut the forest down, that would be really good. Okay, so some folks in the chat asking about installation of the module. Yeah, maybe I should have told you about the module at the beginning of the workshop. That would have been good. Yeah, I'm sorry about that. If I had told you at the beginning, maybe you would have had enough time to install. But you know what? This notebook is available for download, and it'll be available after the workshop. So once you finally get that module installed, you're welcome to try it out on your own. But for now, totally cool to follow along. So now we're going to explore some particular probabilities. So what is the probability that a forest in its youngest state will advance to the next oldest if we wait. So we're asking kind of a complex question, but the answer is totally defined. So we can write P0, 0, 1. So this is wait, and as far as is currently in the youngest state, what's the probability of transitions to the first state? And we get 0.9, or 90% probability. Oh, hey, Srikaran, it's really good to see you. Glad you're liking the workshop. But anyway, so we're going to be going now to what is the probability that a forest in its oldest state will burn down if we wait. So in this case, we are doing wait for 0. The forest is in its oldest state, so that's 2. And it might go to its youngest state, because that's what it means for it to burn down. And that would go 10% of the time. So hopefully those examples give you some sense of what the probability transition matrix is useful for telling. Okay, now we're going to explore the rewards matrix. And we can print out the rewards matrix here. And we see that it has 2 columns and 3 rows. The 2 columns are for the different choices you can make as the forest manager. And the columns represent the rewards you get from each state. So let's look at a research question. What reward do we get if we choose to wait and the forest is in its oldest state? We can get this information by multiplying the state, which is this vector on the right-hand side, which is the oldest state one. We can multiply that with the rewards matrix at its state 0, which is the wait state. So we multiply the wait reward with the state profile, and we get 4. So that tells us that $4 will be given to us if we wait and the forest is in its oldest state. But if we choose to wait and the forest is in any other state, so I've just kind of, I should really maybe do this in 2. So this is the youngest one here, and then this would be the next youngest. So here's the youngest state. Here's the middle age state. So this is S1 and S0. And yeah, so we get 0 in both cases. Oh, someone is saying in the chat. Oh, Armand says the GoDaddy promo code expired. I will let our team know about that. Yeah, that should not happen, I don't think, because it's Global Hack Week. But I will look into that for sure. I'm glad you're enjoying the workshop though. So let's look at what the reward we get if we choose to cut and the forest is in its oldest state. So if we choose to cut the forest, we get $2. And if we choose to cut the forest and it's in its second youngest state, we get $1. So you can see how this, how these examples work. But now we want to find the optimal policy. So up until now, we've just been looking at the rewards matrix, looking at the probability transition matrix, and kind of playing around really. But now we're going to use Q-learning, which is that algorithm that was mentioned at the very beginning, to optimize and solve for this Markov chain, essentially. And the Q-learning algorithm is implemented in the MDP module of MDP Toolbox. And I'm going to actually share that documentation with you all to show you what this looks like. So we have so many different algorithms. We have this one called backwards induction finite horizon. We have one that's called policy iteration. We have one that's called value iteration. Lots of different algorithms that you could explore. And to be honest with you all, I do not know the details of all of these algorithms. But today we're going to use Q-learning, which is a type of machine learning algorithm, to do this one. And that's using the Q-learning module or method, excuse me. And so that accepts a transition probability matrix, a reward matrix, a discount, which is another factor that we haven't talked about yet. The discount being the likelihood that this relationship will stay in the future, so that in other words, we can rely on this, that it's stable. And so that is the other accepted value. And then we have all these other things that I won't get into, but basically we can use this method to optimize our policy. Let's go back to our code, and you can see in this cell that we are going to pass the P and the R matrices that we created at the beginning of the notebook. And I'm also going to pass a 0.1 discount. And what that means is that we have 10% probability that this relationship no longer holds in the future. So the discount relates to how much we should discount future returns over immediate returns. So in other words, think of it this way. Let's say that your business, your forest management business, goes bankrupt. If that happens, then we can't rely on this system we've built where we have cut or wait. We have to actually sell the farm, and this policy is no longer valid. So then in that case, we need to have a higher discount. So let's continue on with this. And when we define a model, we can run it, and then we can ask for its policy. So let's run this. And we get the following policy. We get that if we are in the youngest tree situation, we should wait. If our tree is in middle age, then we should cut. And if we are in the oldest state, we should wait because we get a bigger reward. So, for example, should we wait or cut in the youngest state? We can access the first index and see that the model thinks we should wait. And then in the second youngest state, it thinks we should cut the tree. And in the third, it thinks that we should wait. So those are the policy results. And so now we're going to look into this a little more. So a 99% discount says that it is very likely that the game will continue into the future. So this is our long-term strategy. And in the long-term strategy, we see that all of our values are wait. So in the long term, the model thinks we should always wait no matter what the results are, because eventually we will have we will show a reward that is really, really good in the long term. On the other hand, if we apply a discount of 0.01, that means that it is very likely the game will not continue into the future. So if that's the case, that's when we get these cut decisions. So that's when the model says, you know what? We have a middle-aged tree here. We can't risk this tree burning down. We have to cut it before the rules of the game change and we're out a tree. So in that case, we apply a cut to the model. We have a cut policy instead of a wait policy. Okay, so yeah, this is a really simple model, but it's really powerful in figuring out what kinds of decisions you might want to make if you're faced with an uncertain future, and a future that could go one way, but it might go the other way. And hopefully this workshop was helpful in introducing you to this new algorithm. I hope that you learned a thing or two, or at the very least that you enjoyed being in the stream. So thank you to each and every one of you for joining. And I'll take any questions that you have at this time. Stick around for a few minutes in case anyone has any questions. Yeah, I see some users saying, got here late, watched it from the start. It's always an option. If you ever get lost in any of our Global Hack Week streams, there's always a rewind button, and make use of it. Yeah, really glad to see you all here. And another suggestion to use Google Colab. That's a really good idea. And I think I might start using Google Colab in my um, in my streams because I think it would just be so much easier to share with you all over Google Colab. But that's kind of something maybe for the future. Maybe I'll try that in some of the computer vision workshops that I've planned. 2939 says, are there any resources to learn more about this? That is a really good question. And let me show you where I was introduced to this concept. I will show you that. And I think that YouTube video has some really good resources. Yeah, so honestly, I think YouTube is probably the best place to go. But let me share this with you. My commute or transportation example is based off of this YouTube video. The professor in this video uses a very similar scenario um, that I just think it's a really good way to understand this algorithm. But there's some papers linked to that, and in the related videos, there's some tutorials. So I highly recommend checking out that video that I pasted in the chat. And Raul, I'm glad you enjoyed the session. Thank you for coming, and thank you for participating in the chat. Best of luck in the Global Hack Week. But yeah, everybody. So at this point, haven't received too many questions, so I think we will wrap up. But it's really, once again, a pleasure to be with all of you virtually, and I hope that you have a great rest of your day. Bye now.